All right, I think it's time to start. Good morning, good evening, or good afternoon. Welcome to join this Topology Optimization webinar. Today is the 7th session. It is kindly organized by Professor Julian Norato from the University of Connecticut. Thank you, Julian. The floor is yours.
Thanks, Jun, and welcome everyone. It's nice to have you all here. And we have a series of very interesting talks for you today. I would like to remind you that the speakers are going to make the presentation, and then we're going to leave in each one of the presentations, we're going to leave a few minutes at the end for questions and answers. You can either type your questions in the chat window in Zoom or in the YouTube channel, and we will be monitoring the question and we will relay to the speakers. But if no one is asking questions, you're also, free to just jump in and mute your mic and ask the question directly to the speaker. So with that said, let's go ahead, and it is my pleasure to introduce our first speaker for today, Dr. Seth Watts at Lawrence Livermore National Lab. Seth, go ahead.
Thank you. Can everyone hear me? And is everyone seeing my slides?
Yes.
Excellent. Thank you. So thank you very much, Julian, for the invitation to talk about my work. Before I begin, I'd like to acknowledge my co-authors on this particular paper, Bill Arrighi, June Kudo, Dan Tortorelli, and Dan White, all of whom are also at Lawrence Livermore. I've got my email address there. I'm very happy to answer questions. If I don't get to any questions that come up during the presentation, please feel free to email me, and I'll have it again at the end of the presentation. So the presentation is mostly based on the first article that I have here, which appeared in Structural and Multidisciplinary Optimization last year. There was a follow-up correction, which is somewhat embarrassing, but I made a couple of mistakes in implementing some modifications to Sigmund's 99 line code. So I'll mention those where it's appropriate in the rest of the presentation where those corrections are made. But so basically the talk is going to be based off this first paper. This last paper is an extension. It appeared in International Journal for Solids and Structures this year, and it extends the results that we have in this SAMO paper to look at more unit cells and some other parameterization things that I will discuss a little bit later. But the primary source is this first paper. So I'm sure everyone here is very familiar with topology optimization. I'll just mention that you can also interpret topology optimization as, rather than a solid void type of design, it's a material design. So we're actually choosing or assigning the constitutive response throughout the design domain. I'm showing that here as the elasticity tensor as some function of a density field or some decision variable field, and that's we set up some sort of interpolation, and then what I'm showing here is just the very standard linear elasticity, doing minimum compliance design subject to a resource constraint. And the traditional approach is to choose some sort of nonlinear parameterization that's used for the physics, SIMP being the classic example, where we have a nonlinear interpolation between some void properties and some solid properties for the elastic response. And then we have a linear interpolation when we evaluate the resource constraint so that mixtures are inefficient. And as a result, you get 0-1 types of designs. And this is the result from Sigmund's paper back in 2001. From the 99 line code. This is design of a beam and 3-point bending. I'm sure everyone's familiar with that. More recently, I think the rise of additive manufacturing has expanded the feasibility of producing what I'll call kind of custom or one-off structures, where to at least the bumper sticker is that we can print anything we can design, and that's not quite true, but I think we're approaching that. And so there's been a lot of interest in designing topology optimized structures, then additively manufacturing them. And I believe we have some talks later today on that very subject. But an additional capability that additive manufacturing has brought with it is the ability to produce very fine scale designs. And I might be slightly biased here by working at Lawrence Livermore, where we do a lot of work, at least in polymers, in producing very fine scale structures. So I have this example here. This is taken from a paper by Chen in Science Advances from last year. This is a lattice of 4 by 4 by 4 unit cells. The entire thing is is a 1 millimeter cube. So we have 250 micron unit cells, and these are about 30 micron struts. Now, I'm not going to say that we can produce something the size of a car with features that fine today, but I think the scalability of this type of thing is only going to expand in the future. So the point being that we have the ability to fabricate at this really fine scale. We should be able to design at that type of fine scale. When you have such fine scale features at a bulk scale, the response of the microstructure looks at the macro scale like the response of a homogenized solid with particular properties. So I'm showing here, this is the same physics, linear elasticity I was showing on the previous slide, except now instead of having a pointwise elasticity tensor, we have a homogenized tensor. This governing equation works at the macro scale only. We have the homogenized response of a fine scale structure. The second box shows the way that you can evaluate the homogenized response when you're given the design. And these characteristic equations, chi-ij, come from solving what are called cell problems. This is in no way new. I certainly did not invent this. This is a standard approach for elastic homogenization. But the point being that if you have a fine scale structure that you can evaluate its homogenized response and then solve a bulk scale problem more simply. You don't have to resolve fine scale features. One major upshot with this is that if you have a structure like this, you can have a density that's somewhere intermediate between 0 density void and 100% full density. You could have something which is 75% dense, and there are structures that will achieve that in a homogenized sense. And so you no longer have to drive your designs to pure 0, 1. If you end up converging to, say, 75% dense in a location, you have a microstructure that can achieve that. So the really full power way of designing optimal structures like this is kind of a full topology optimization, do a macro scale topology optimization, and also micro scale topology optimization. So at every point in the macro domain, you can design an optimal microstructure. That's certainly been done. It's been described in the literature. The trouble is it's expensive, especially in 3 dimensions. And it's just an expensive problem. So we'd like to do something that's a little bit cheaper so that we can do it more regularly to solve kind of everyday problems. And we're going to take almost a polar opposite approach. Instead of having a full design space everywhere in the microstructure, we're going to have a very low dimension, and in this paper, even just a 1-dimensional design space at the micro scale. So what we're going to do is to choose a microstructure ahead of time and allow it to vary in 1 dimension only. In this case, we are choosing these open truss microlattice types of architectures, and we're going to allow the rods to vary their diameter. They're all going to scale in the same way, so there's only just the one controlling parameter. So there's a couple advantages to making this sort of simplifying assumption. One is you can pre-compute the response. You don't have to compute it during your optimization loop. You can do some sampling and modeling ahead of time, which is what we do here, save that model, and then when you want to do your macro scale, or sorry, multiscale topology optimization, you can just reference your surrogate model and you have the results almost instantly. It's also well matched to using what I'll call known printable microarchitectures. So looking at this picture, this is what I'm calling an ORC truss. We know we can print ORC trusses. And so if my entire structure is made up of ORC trusses, then at least a first order, I can guarantee that I can print that. I'm sure people that know more about additive manufacturing are wincing when I say that, but at least a first order, I can guarantee that I can print it without having to impose manufacturing constraints. And also, I can ensure that if the entire structure is made out of one type of unit cell, that there will be connectivity everywhere between different unit cells. I don't have to worry that I might have a unit cell in one element and a different unit cell in a different element where the solid parts of those unit cells don't overlap. I can guarantee that a priori that there will be a connected design. So that's nice from a fabrication standpoint. And I'm showing here, this is the sort of rod scaling that I'm talking about here. So from very low to very high volume fraction. And this is an Ashby chart showing density on the x-axis and Young's modulus on the y-axis. And these points that I am showing here are actual homogenized Young's modulus values on this thing. So these are the kind of, I'm going to say, the real response of the homogenized material versus this dashed line, which is what we assume in SIMP. So the scaling is not a uniform exponent. It depends on the density, and it's not as steep as we typically assume in SIMP. This is a slope 3 or an exponent of 3 for the SIMP value, and this asymptotes to a value of 1 actually at low volume fraction. And so in the first paper, the main source here, I am considering models for these 3 types of truss lattices. I have isotruss, an ORC truss, and an octet truss. And I should mention, so I'm absolutely agree. If anyone has an objection that I'm leaving performance on the table, yes, I completely acknowledge that. These trusses I'm in no way claiming are optimal microstructures. However, they're known printable, they're relatively simple, they're easy to parameterize. So I have a very simple modeling job, and I can do a fast macro scale design, but I acknowledge this will not be the best possible macro scale design. It will just be an efficient one to obtain. So I should also acknowledge we are not the first people to do surrogate modeling or to do optimization with predefined microstructures. In fact, the very first topology optimization paper did that with defined arrays of holes. So this is not new. This particular implementation is, but the idea itself is not. And in terms of surrogate models, there are many models in the literature. They tend, however, to be based on rod theory or beam theory. As a result, they have nice, simple analytical forms and are easy to implement, but they tend not to be particularly accurate. And the reason for that is that rod and beam theory don't actually model the nodes where the struts join together. They're just points in space where boundary conditions are imposed on the rods or beams. And as the volume fraction increases, the size and effect of those nodes becomes non-negligible. Other assumptions, like in rod theory, you typically assume that the nodes can't transmit moments into the bars. As the nodes become larger, that assumption becomes less true. And as a result, the accuracy of the models decreases. So one of the results in this paper was we looked at to what, like how dense of a structure are these analytical models accurate for. And it depends on what you want to consider your standards for acceptable accuracy. I think as a general rule of thumb, about kind of 2 to 5% volume fraction, these rod theory based surrogate models are accurate. But I'm showing here, this is kind of not fair to the surrogate models because I'm showing over a full range of volume fraction. The canonical paper on the octet truss, which these results come from, is the one by Deshpande and co-authors. This is from 2001. I'm sorry, I forgot the citation. But it actually predicts linear stiffness and no influence whatsoever on the base materials Poisson ratio. That's the blue lines on these plots. So in both cases, the density is on the x-axis. Here I'm showing Young's modulus, and here I'm showing the Poisson's ratio of the homogenized material. And you can see that the stiffness is certainly not linear, and there is certainly an effect of the base materials Poisson ratio. So the simple models don't capture those effects. So the goal of this paper was to create more accurate surrogate models that are hopefully almost as simple as this, so that they're still easy to implement, but that are capturing the real response of these types of microarchitecture materials better.
Seth,
so yes.
Sorry to interrupt, but just wanted to let you know that we have about 2 minutes left. So
oh, wow, okay. I certainly love hearing myself talk. I will go very quickly then. Thank you, Julian.
Okay, thanks.
So the basic approach, I'm sorry, I spent too much time on the introductory material. The basic approach was to generate very highly refined continuum finite element models of these types of structures. This is based on adaptive mesh refinement, sample the design space, and then generate surrogate models. all of the truss lattices we looked at had cubic symmetry, so we only needed to model 3 elastic moduli, which simplified the job. They have these very simple model forms. They're all just simple polynomials. Even though they're quite simple, they generally fit the data fairly well. The data is all in appendices to the paper. So if you don't like my models, you're certainly welcome to create your own. I make no claims that my models are the best possible ones. They just happen to be simple and have continuous derivatives and fit the data relatively well. The reason I wanted simple models like that is it's now simple to modify. I'm going to claim any topology optimization code to use those surrogate models. So if you can do standard SIMP, nonlinear interpolation, I claim that you should be able to use these surrogate models and design these types of multiscale structures. It's just going to, there are slight differences in the actual implementation. I won't get into the details, but basically instead of doing an interpolation of a solid isotropic elasticity tensor, you generate your own based on these models. That's really the only difference. Everything else in the optimization remains precisely the same. And when you get a converged density field, it's quite easy, especially if you have a Cartesian grid, like the 99 line code does, to recover the actual raw definitions and get a structure which you can print. I didn't include pictures, but we have printed structures like this. That's certainly doable. Getting to the conclusions, if you move to these types of microlattice materials, you can improve your compliance design results modestly. It's not a huge improvement. It's also not a guarantee that if you have a microstructured material that you will improve your design. We showed some that are essentially a wash, that were no better than just doing SIP design. And depending on how you limit the microstructure you're considering, you can actually make it substantially worse. Another thing I should emphasize is that the truss lattices generally are anisotropic. The orientation of the lattice, therefore, is an important consideration for the design as well possibly as for the manufacturing. And also different unit cells have different isotropies. They will have different orientations. So there's a consideration to be made about which specific unit cell you would like. You can also have more than a one-dimensional design space at the microstructure. The third paper that I mentioned in IJSS looks at a two-dimensional design space where the only thing that we've changed is considered hollow rods. There's a lot more performance that results from that. And so just my last slide to summarize, when you move to design with surrogate models, you no longer have to drive your designs to 0-1 to have a design that you can interpret and fabricate. You can ensure by construction the continuity of the design and at least in some sense the manufacturability of it. Using surrogate models that have been provided, if you don't have to generate them yourself, you can do almost similar costs to traditional SIMP. You can have modest performance improvements. There's additional performance that can be got by more sophisticated models. And the last thing is that even though I've demonstrated this for elasticity, you can certainly do this type of homogenization and modeling for other physics like conductivity, fluid flow, and the like. I apologize for going over. I'm happy to answer questions now, or again, there's my email address. I'm happy to answer them online. Thank you very much.
Thank you very much, Seth. And we do, let's try to take a single quick question. There is one in the chat from Dirk Monroe. And it says that one could introduce an additional variable in a multi-material-like formulation to select different microstructures in different elements, maybe with a special load carrying capacity, for example. And I guess it says it is a question, so I guess
yes, no, I can
correctly. I guess the question is this possible? Do you think this is possible?
I think it absolutely is. I think it's completely analogous to traditional multi-material design. You're just choosing a different constitutive model that you interpolate between several choices. The one downside I see with that approach, however, is you would need to take some care to guarantee that you would get a continuous structure. So if you have, let's say, an ORC truss in one unit cell and your optimization has chosen an octet truss in the neighboring one, can you necessarily glue those together and get a continuous structure? I think that you could do that with some care, but it's less guaranteed than if you only have a single case, a single unit cell.
All right. Well, thank you very much, Seth. This was very interesting. And in the interest of time, let's move on to our next presentation, which is by Tsuyoshi Nomura from Toyota Central R&D Labs. So Tsuyoshi, if you could please share your screen, and the floor is yours.
Okay. Yes. Can you see my screen now?
Yes, we can. Go ahead.
Okay, good. So, hello everybody. So I'm Tsuyoshi Nomura from Toyota Central R&D Labs, and this presentation is actually already presented in 2018 in WCSMO 13, but I added some new result at the end of the presentation. So please enjoy. Okay. So the background is that so recently there are many continuous fiber deposition technologies proposed, such as continuous fiber printing in the here, like say like Markforged 3D printers, or say there are another technology so-called fiber tailored fiber placement that is using the machine-controlled embroidery machine, and another technology is so-called free motion printing. That is an extension of the continuous fiber printing by using the multi-axial robot arms, and the last one is automated fiber placement, tape placement technology, and that is very well-established technology that is sometimes used in to fabricate passenger airplanes, and that kind of technology is used to create fabricate a composite material that allows the fiber orientation controls locally, and that kind of composite is called variable axial composite. And I want to build a optimization technique to design such new composite materials, structures. So my objective is to create a versatile anisotropic topology optimization technique, and it should be applicable to not only the structural mechanics, but I want to solve many other physics as well. And I want to make method dimension independent, so that you don't have to prepare one method for 2D and the other method for 3D. I want to propose a unified formulation. And yes, and I wanted to observe the mutual coupling of the topology and orientation, and that is the goal of my objective. So the problem I want to solve is that, as shown in here. So I want to design the ordinary topology optimization that optimize the layout of the density, and also I want to optimize the local orientation of the material at each point in the design domain. That is the objective. So, I want to emphasize 2 points in this presentation. And one is the tensor-based orientation parameterization, and that uses a orientation tensor. And orientation tensor is decoupled from the physical properties, so that you can apply the same technique to other physics. And another point is that in order to use a tensor as a design variable, you have to consider many pointwise constraints. But I wanted to avoid that, so that I remove that constraint by utilizing the projection method. So I want to move to the formulation part. So The topology optimization is very conventional one. That is using a Helmholtz type density filtering with Heaviside projection, and that is proposed in 2011 by Atsi and Professor Razloff. And I'm following the Atsi's formulation that is that start with level set function and use a Heaviside projection to obtain the characteristic function chi, and we also the phi is filtered using the Heaviside Helmholtz equation in equation 2, and it is projected to as a row using the Heaviside projection. And I think this is almost the same method with other ordinary Helmholtz filtering and Heaviside projection method. But it has a little bit different notation, but essentially they are the same. And in order to handle the anisotropic property, I little bit modify the SIMP to handle the anisotropic property, so that say this method is can be said SAMP. So anyway, so I interpolate the stiffness tensor using the density, but the stiffness tensor itself is anisotropic, and anisotropic that is written in CS in equation 4, and the CS is interpolated using the orientation design variable that is tensor-based orientation design variable. And so the reason why I use tensor for the orientation variable is that the material property is a pseudo vector, so that ordinary angular three-dimensional angular representation is not perfect for that. For instance, if you use the Euler angle as a design variable, you will have a singular point as the, say, North Pole and the South Pole, and you will have a duplicated design variable in the North same sphere and the South same sphere. So if you use the tensor design tensor representation, you can remove all of these inconvenience. So the tensor I used is a so-called orientation tensor that is usually used to analyze distributed orientations with by having a probability function. However, in our case, I just want to represent a single orientation at a point, so that we can assume that the probability is always 1, so that the design tensor becomes very simple, as shown in equation 7 and equation 8. So basically, that is a self-dyadic of the orientation vector. And by using this orientation tensor, we can interpolate the transverse isotropic tensor using this tensor, as shown in equation 9. This looks a little bit complicated, but essentially it is very simple, because, say, except for the first term, everything is just a linear combination, and the first term is still yet only quadratic interpolation. So it is basically a very simple way to rotate the elastic tensor. And so I introduced, so that I defined the design variable, orientation design variable Q2, as shown in equation 11. That is 3 by 3 rank 2 tensor, and we use a upper triangle that is 6 elements as a design variable, and we filter it with Helmholtz filter, and we use another projection to the off-diagonal part. And we also, in order to make the design variable as a tensor, we constrain the 3 tensor invariants. That is a tricky part of this method, but anyhow, we can simplify this constraint as shown in equation 15 and this equation 18, and this is a formulation. So this is very simple stiffness maximization formulation. That is, we just want to minimize the simple objective function with respect to design variable that is phi, that corresponds to the density, and q that controls the orientation. And we also apply the volume constraint, and we in order to make the orientation design variable tensor, we constrain the tensor invariants using the equation 19e and f. And I don't think I have enough time to describe all of the details, so I want to move this part very quickly. But basically, I make a trick on the projection method in order to remove the pointwise constraint. And in the projection, I use isoparametric shape function as shown in here, so that we can squeeze the coordinate in cubic coordinate into the tetrahedra, so that we can keep the trace of the tensor less than 1. That is a trick, and this can be applied to the 2-dimensional problem as well. And and I also use another projection to keep the second tensor or invariant constant. So, and I want to move to the numerical examples. And the first one is multi-load problem setting is in planar structure. And I want to compare single loaded formulation and multi-load formulation to show its capability. And basically, it works okay. So left column shows isotropic topology optimization, and the right hand side, left side column shows isotropic topology, and the right hand side shows anisotropic topology, and the top row shows single loaded case, and the lower row shows multi-load case, and it works okay. Everything works okay, and it shows a little bit better performance by using the anisotropic topology optimization. Yes.
Tsuyoshi, sorry to interrupt. Yes. If you could please wrap up in maybe a couple minutes, that would be great. Yeah, thanks.
Okay. Yeah, so, and this is another example, and this is a famous MBB beam problem, and we can also solve the problem without issues. And the third one is thermal problem, and with different filter radius, which uses a very large filter radius in the orientation design variable. and it shows a coupling in between the anisotropy, density and orientation. And yeah, so I want to move very quick and okay, so I want to switch up. Okay, so and finally, I want to show some practical example. So I designed some automotive parts using this method, and I tried the fabrication using a tailored fiber placement technology that uses numerically controlled embroidery machine like this. And the problem is sports car rear wing pillar structure. And this is a boundary condition, and this is a topology result. And we also obtain the orientation inside of the structure simultaneously. And we use some tricks to dehomogeneize the structure, and we extract the fiber path, and we fabricated the structure using the with collaboration with IPF. And this is a final product, and this is I think this is very cool. And I also did the experiment, and the result shows that the original part weighs 425 grams, but the prototype is only about 120 grams. That is almost the 1/3 of the original weight, with the same structure performance. That is unbelievably good. And finally, this is only showing only the result, but we are trying very complex 3D structures as well. And yes, it works okay for this kind of very practical complex problem as well. These problems handles 7 load cases, so but still it worked okay. Yes, that's it.
Thank you very much.
Yeah, this is the conclusion. Thank you very much.
Sorry. Yeah. Thank you very much, Tsuyoshi. Maybe we can take a quick question. Does anyone have a question? Maybe you can write it in the chat or unmute your mic and ask. Okay, so I have a quick question, Tsuyoshi. So for the designs that are like the 2D designs, so it looks like you have a single reinforcement, right? So this wouldn't be necessarily like a laminate where the different laminae have different fiber orientations, and if not, is that something that you think that your method could maybe accommodate in the future?
Yes, actually, yes, I think that is only the matter of the resolution. So, but indeed, actually, so now it is all. Everything is solved with only a single solid structure. But in the future, yes, as you mentioned, it should be wonderful if we could design the laminated structure. So the brute force method is just to increase the resolution of the optimization, but there may be much better way to handle such kind of situation. So, yes.
Okay. Well, thank you very much, Tsuyoshi, and particularly thank you for, this is very, very late for you. So we're very thankful that you stayed this late to present to us your wonderful work. So let's move on. Our next presenter is Professor Mattias Schevenels from KU Leuven. Mattias, if you could please share your screen and take the floor, please.
Okay, thank you, Julian. Can you see my screen?
Yes, we can. Yeah.
Okay, so I will talk about topology optimization of support structure in additive manufacturing to account for thermal deformations. And this is actually work done by Jeroen Pellens, who defended this PhD thesis in our group in the beginning of this year, together with two people from Materialize, the 3D printing company here in Leuven. So we focused on metal-based additive manufacturing, and this slide explains the process that is followed in selective laser melting. The figures on the slides explain the different steps in the process. So here we start with the build plate, and there is some metal powder on the build plate. It's deposited by means of a recoater. That's this thing here. Then we have a laser that traces the first section of the part. It makes the powder melt, and then it solidifies and then becomes the first layer of the part. Then the build plate decreases, a new layer of powder is added by the recoater, and the laser passes again. So this is repeated until the part is built. But during the passage of the laser and during the melting of the material, the temperatures will become very high. The material, once solidified, will shrink. It will deform thermally. And in a structure like this, with two cantilevering parts, that may lead to an upward displacement of the two tips here. And that might be a problem. Not only does it lead to inaccuracies in the final printed part, so 3D printing companies want to avoid it for that, but also it may lead to the problem that is illustrated here. If the upward displacement of these beam tips is larger than the layer thickness, then it may lead to recoater collisions, and then the print will fail, because due to this collision, the part will move, and then you cannot use the print anymore. So we want to avoid that during printing. And in order to avoid that, support structure is added to the print. So the support structure is sacrificial material. It's removed afterwards. And it serves three goals, in fact, or at least three goals. First, it provides support for the horizontal layers or overhangs during manufacturing. So that's the first reason to include these supports. Second reason is to improve heat transfer to the build platform, as they represent ways of high conduction towards high thermal conduction towards the build platform. And then finally, they also connect the part to the build platform and will reduce or restrain these vertical displacements that can cause recoater collisions. And the support structure is often printed as a lattice structure. So that's also the structure that is suggested here. Now, in current 3D printing practice, these support structures are designed manually. So engineers look at the design, they try to estimate where the largest deformations will occur, and they will include a lot of support structure at that location. So that's a lot of engineering work that has to be done. The structure is probably also oversized in the end. It can be smaller in terms of material use. And due to this excessive use of material, the printing time will also increase. And finally, after the part has been printed, there is a post-processing step. The support structure has to be removed, which is a manual process. That's also costly. And then the surface of the printed part has to be post-treated. So we wanted to use numerical optimization to improve the design of the support structure, so that at least the engineering time in the beginning is reduced, and also the amount of material in the support structure and the printing time is reduced. So in order to optimize the support structure, we first have to simulate its thermal behavior. And to do that, well, we assumed that it has a lattice structure. And we used, in fact, the equations that Seth just presented in the first talk of this session to model the support structure as a homogenized lattice with the isotruss layout. So by doing so, we choose a density for every unit cell throughout the support structure. And this density then translates to a homogenized Young's modulus, a homogenized Poisson's ratio, and it also gives us the diameter of the bars. And then we simulate the thermal deformations using the so-called inherent strain method. So we assume that the part is built in a limited number of stages. We will not model every individual layer because they're way too thin, so we don't want to do that many simulations. So we collect a large number of layers in one stage. For example, in this figure here, 5 stages are suggested. Then for every stage, we impose thermal strains in the top layer, in the top part here. And we calculate the corresponding displacements in the entire part, or in the entire part that has been printed so far. So we repeat that for every stage. Now, this is not identical to reality, because in the reality we have thinner layers and the heat is much more concentrated at the top probably, but we can fit the initial strains that we impose here in the top layer to experimental results determined on the printer of interest for the material of interest and the printing strategy of interest. So we did that, and we used the numbers for the initial strains that Materialize provided us with. And this slide here demonstrates the simulation of these thermal deformations for a simple part, so a part with a cantilever. And the gray area here is the homogenized support structure. And of the different stages. So every stage is a finite element calculation, and for every stage we find a displacement, and we will monitor during the optimization the upward displacement of a number of output points at the top of that stage. Oh, okay, so then we arrive at the formulation of the optimization problem. So as I said, the design variables will be the densities of the support structure for every unit cell or throughout the entire support domain. First, we apply a density filter to these densities to avoid abrupt changes of bar diameters. Then the objective function is the total volume of the support structure. And we include some constraints to limit the upward displacement of a number of output degrees of freedom. So at the top during every printing stage. So that's mathematically, that looks like this. So this L is a selection matrix defined for every printing stage I and every output degree of freedom J that will monitor a certain degree of freedom. Okay, so these are some results obtained for the same cantilever structure of before. So here at the bottom, we have the optimized result that we obtained, where we imposed a maximum allowable displacement of 1.5 micrometers, as that is the layer thickness for the printing process that we consider. And it led to a structure that you can see here. Here at the end of the cantilever, we observe some kind of a column or a strut that will prevent the tip of the cantilever to move upwards, as I showed in the previous simulation. So the upward displacement will be restrained by this thing here. And then we also observe larger bar diameters in this area here. And we think that this part acts as some kind of a shear wall that prevents shrinkage of the entire cantilever, as this shrinkage would lead to a movement to the left of this point, and so to bending of this strut. And this bending would lead to an elongation of the rightmost fiber of the strut, which would result in an upward displacement. And all that is prevented or restrained by this shear wall-like structure. This figure here shows a design that consumes the same amount of material. So this 16.2% of the design domain is the volume that we obtained after optimization. Here we started from the same amount of material and we distributed it uniformly over the design domain to simulate a very naive manual design. And then we see that the largest upward displacement over all printing stages is more than 2 micrometers, so it becomes too large. And here we can see an animation of the displacements during all printing stages. So if you compare them, then you can see that the upward displacement here is slightly larger than the upward displacement here. And here is an indication of the layers where the maximum allowable displacement is exceeded. So here that is the case, and here it's okay. It's never exceeded. And then finally, we also applied the method to a 3D example, which is in fact just an extruded version of the 2D example that we just considered. And then it also works. So the next slide here shows an animation of the different stages. And we can see the same strut-like structure here at the tip of the cantilever and a similar shear wall-like structure here. Okay, so that brings me to the conclusion of this talk. To summarize, we modeled the support structure in SLM printing using a lattice structure that we homogenized, and then we used the inherent strain method to simulate the thermal deformations. And the results showed us that this method works. It leads to quite light structures that consume a small amount of material and that comply with the constraints that we imposed, at least according to our simulations. We did not validate it by means of experiments yet. Okay, thank you.
Thank you very much, Mattias, and thanks for your timing. So we have time for questions, and there is one already in the chat, actually two from Dirk Monroe. The first one is, what is the computation time roughly on the cantilever example, including both process simulation and adjoints?
For the 3D case, it was about 4 hours, and but it's quite a coarse mesh. In fact, we only used 150 elements lengthwise, and then 20 by 20 in the other dimensions, and then it was 4 hours on a laptop. Okay.
And the other question from Dirk is, how confident are you in your interpretation of the results? So is the algorithm convergent?
What's the last part of that question?
Yeah, it says how confident are you in your interpretation of the result? Is the algorithm convergent? Dirk, if you would like to, you can unmute your mic and maybe clarify.
Yeah, I can elaborate. So yeah, so you provide a very good interpretation of the support structure generated by the algorithm. And the question also comes from the fact that I know from experience that those sort of problems are more difficult than the standard minimum compliance problems, in terms of how the problem behaves. And I mean, to be very blunt, I could say, hey, is your interpretation of the support structure correct? So in terms of a shear wall, etc., or is that just is that just a weird, a failed algorithm result? You know what I mean? It didn't converge properly to some.
I have no proof that is the correct interpretation. We did not remove the shear wall-like structure to see if it behaves differently.
Okay, and well, what I would guess is to do sort of run a bunch of cases with random starts, see if you can make some sort of sense of do you consistently converge to that? Is that a good solution? You know, for example.
We applied the method to other cases as well, which are included in the paper, and there we can also give an interpretation that at least is to some extent logical.
No, fair.
So we did not use different starting points, but we considered different cases.
I had a question, Mattias. It seemed like in your optimization formulation that the number of constraints will explode as you have more layers. How do you actually treat this displacement constraints?
We did not aggregate them here. We limited the number of output points in our case. So we do not take every degree of freedom at the top of the design, but we skip some points. And then afterwards, we check if it's okay at the intermediate points. And then you could think of an adaptive algorithm that includes problematic points in the next run. But we did not use aggregation in this case.
So right now you are actually solving a lot of adjoint problems?
Yeah.
Okay, thank you.
All right, thank you very much, Mattias. A very, very interesting presentation. Let's move on to our next speaker, who is Professor Natasha Vermaak from Lehigh University. So, Natasha, if you'd like to share your screen and take the floor. And I don't know if...
Okay.
Okay, yeah, we can hear you. Yes.
Okay, great. So thanks, Julian, for inviting me and for this opportunity. My name, again, is Natasha Vermaak. I'm Associate Professor of Mechanical Engineering and Mechanics at Lehigh University. And I'm going to give a teaser presentation based on the work and paper shown here of my PhD student who recently graduated, Dr. Shoujia. She's pictured. The title is Topology Optimization of Tribological Composites for Multifunctional Performance at Sliding Interfaces. And this work was a collaboration between my lab and experimental tribologists, Professor Crick, and was funded by the NSF in the US. So before I jump in, I just briefly want to emphasize that in my lab, we acknowledge the fact that science is real, love is love, Black Lives Matter, feminism is for everyone, immigrants are welcome, and we believe that materials design is cool. This banner was adapted from Sami Kata. And my group has a particular research focus on thermostructural design, materials degradation, and durability. So today's topic, composites, are already widely used in tribological applications across energy, biology, and defense sectors. However, their design is mostly trial and error and based on legacy. If you're not familiar with tribology, it's the study of surfaces in relative motion and includes the topics of friction, wear, and lubrication. We care about wear and friction because the costs are huge. They impact energy consumption and the environment. We also care because they're often major limiters to system performance. Example applications are automotive clutch facings and brake linings. Example composites include metal polymer and metal ceramic systems, which have been shown to improve friction and wear performance, as well as having interesting multifunctional capabilities. Some are listed down here. So knowing that the design of tribological composites is currently trial and error, my group introduced the combination of TO and tribology in 2017, and the focus of today's paper is exploring the multifunctional performance of these tribological composites. So to better understand how TO can help transform design for wear and multifunctional wear, I have some basics for you about the wear process itself next. We focus on linear abrasive sliding wear. So imagine a composite sample, this gray block up here in the top left. There's a normal force applied, and it is sliding back and forth along a polymer, a PDMS, countersample at the bottom. The countersample has some abrasive paper on it without lubrication. So the main things you need to know about wear are shown in these schematic plots at the top right. We care about the amount of material volume loss against, and we plot that against sliding distance. And the slope of this curve, the volume loss versus sliding distance, is the wear rate. And that's plotted separately on the right. A high wear rate means we're wearing a lot, we're removing a lot of material, and it is not wear resistant. The other key feature that is shown is there's always a transition from a transient run-in regime to a steady state regime. Run-in starts out with a high wear rate, which keeps decreasing until the steady state is reached. So taking an example from our experimental work in our team, we have a composite surface. It is a metal polymer, so aluminum in black and epoxy in gray. I'm going to zoom in at the center unit cell of this periodic composite. And what you see is that during wear sliding, the surface profile was measured, and a movie of the relative height map is shown on the right. You see features develop that match the material distribution. Aluminum parts remain high in red, while epoxy wears away more and becomes recessed, so it's blue. The last important physics to mention today is that with sliding, we can also have significant frictional heat. That heat can make wear worse or induce other failures. So the opportunity for design today is combining the concepts and tools that are already very mature in TO for heat transfer with the work we introduced in TO for simple mechanical wear. As a first step, we're looking at maximizing the dissipation of frictional heat generated at the sliding interface of a bimaterial composite during wear, while maintaining some target steady state wear performance. We want to maintain that target steady state wear performance in order to ensure an acceptable lifetime of a component. So in simple words, our first step is a thermal optimization with a wear constraint. To do this, we need a mathematical model for wear. I'm going to briefly list the main ingredients of our wear model, but more details are given in the references listed, and our model has also been experimentally validated in these references too. So first ingredient, we need a parameter to quantify a material's wear resistance. That is the wear rate K. Again, a higher wear rate means we lose more material during wear. Then we use the most common wear law, that's Archart's wear law, to get an expression for the local surface height as a function of sliding distance, local contact pressure, and wear rate. We then add a Pasternak elastic foundation mechanics in order to get analytical solutions for the local contact pressure. Together, we get a well-posed parabolic PDE as a governing equation for wear. And the most important thing you need to know for today is that by examining our model, we've previously shown that the steady state composite wear rate is dictated by the area fractions of the constituent materials at the sliding interface only. Transient run in wear is a different story, but today I'm sticking with the simpler steady state. So in other words, if you know the area fractions of the constituent materials of your composite at the sliding interface, you can predict the steady state wear performance, the steady state composite wear rate. This is very convenient for imposing wear constraints. And again, the run-in wear is a different story and depends on the topology and material distribution. But the steady state can be a simpler problem. So next, we add a thermal 3D model for frictional heating. We apply the standard heat equation with no volumetric generation and make it steady in omega, the body one, the composite. At the sliding interface, we apply a surface frictional heat flux boundary condition that's entering the composite body one, and we use that to solve for a 3D temperature distribution. Note, the frictional heat flux at the sliding interface is a function of the sliding velocity, the coefficient of friction, and the contact pressure. So in essence, this problem is design dependent for that reason. Thermally, we considered a number of case studies with different boundary conditions. I'm just gonna highlight one of them today. The design domain is in green on the right. So the entire system starts out at room temperature. The top surface of the composite body is in contact with a heat sink, not shown, so that the temperature is fixed. The four sides of the body are convective with the ambient air. Then the upper part of the design domain, light green, allows for free material distribution within the material volume fraction, free material distribution with a fixed material volume fraction constraint. We're gonna look at a metal ceramic system and that we have a 50-50 volume fraction constraint. To impose the wear constraint, the dark green part of the design domain is set as a wear layer. In the wear layer, the material distribution is forced to be the same as whatever is decided at the sliding interface through the thickness. The area fraction at the sliding interface is also 50-50 for metal and ceramic. There is no pre-assumption of the material arrangement or distribution at the sliding interface. We're only fixing the surface area fraction in order to ensure an acceptable target steady state wear performance. So as a starting point objective, we're going to minimize the average temperature rise at the sliding interface. The example I'm showing is, again, metal ceramic. That's commonly used in automotive components like disc brakes, pistons, cylinder sleeves. In this pair, the metal is more conductive. less wear resistant, has a lower coefficient of friction, and as a result, it generates less heat comparatively, less frictional heat. Whereas the ceramic is less conductive, is more wear resistant, has a higher coefficient of friction, and thus generates more frictional heat. We then apply a classic density-based SIMP approach for the thermal optimization case with a wear constraint. The workflow, TO workflow, is on the right. And during each optimization iteration, the frictional heat flux is recalculated according to the current material distribution at the sliding interface, which is subject to change throughout the optimization process. Here are the results, and just for a teaser of the results, remember the volume constraint was 50-50 everywhere for this metal ceramic composite. What you see on top is the optimal design in an exploded view. So you see the metal portion of the composite only in blue and the ceramic portion only in yellow. So they're separate. Then what we really care about for the objective function is the interface. So the composite design at the interface is on the left, and the resulting steady state temperature profile is on the right. Finally, the optimal design is compared to a reference composite system. That reference is also 50-50. The reference composite is based on intuitive designs from tribologists for metal ceramic composites that have the less conductive material with the higher coefficient of friction, the ceramic, on the convective boundaries at the outsides. And in that comparison, the optimal design gives a 55% improvement. So let's take a deeper look at the metal composite case, looking at the interface here. Metal ceramic case. The metal is placed at the center. The ceramic, where there's more frictional heat generating, is placed along the convective boundaries. There are also small metal inclusions distributed in the ceramic at the edges. These end up forming connected root-like conduction paths through the height of the structure at the four corners to the top surface heatsink. And these metallic interfacial inclusions also increase the contact area between the two materials, which enhances the heat conduction from the ceramic to the metal. So more detailed analysis, explanation, cutaway views, as well as many more case studies are given in the paper, which we hope you will check out. But to briefly summarize, the paper has presented the first steps towards multifunctional tribothermal optimization for composite design. We started with thermal optimization with a wear constraint. We also did sequentially coupled wear and thermal optimization, but there's plenty more work to do for the future in simultaneously optimizing wear and frictional heat dissipation. We'd also like to focus on the transient run-in wear, where there's more dramatic material loss, changes in contact pressure, surface profile, and of course, add manufacturing constraints. So with that, I'm happy to take any questions. Here's my email. Also, you're welcome to contact Dr. Jia, the first author. She may give faster replies because I'm actually about to give birth any day now. Thank you.
Thank you very much, Natasha, and thank you too for helping us stay on time. We do have some questions in the chat. One is from Krishna Ash, and he's asking whether it would be possible to use these supports as a conduit to conduct away heat from warp critical areas.
Maybe they could come online and help explain the question a little bit more. I'm not sure
Yes.
that I
So
I'm sorry about
Krishna Rash, if you wouldn't mind maybe unmuting your microphone and
can you hear me?
yes, but it's a little bit tenuous. Maybe if you wouldn't mind raising the volume of your mic, that'd be great.
Yes, so I'm quite sorry about that. That was actually meant for Professor Schevenels for his previous presentation, not for the present presentation. Sorry about that.
Okay. Yeah, thank you very much, Krishna Rash.
That's okay.
We have a question from Mohammed Tariq, and it's how accurate are tribological models in practice?
That's a very good question. So sometimes tribologists like to tell me that the field is like the Wild West in terms of constitutive and phenomenological models that are available. In our case, we have specified the type of wear so closely, so linear, abrasive, sliding wear that's dry. And we have also performed our own experimental validation. So in our case, the models we have used have been shown to be quite accurate for this type of wear. But again, there's wet sliding wear, there's reciprocating wear, there's many other types. And I think there's a lot of opportunity for mechanicians to partner with tribologists to provide kind of more modern and new approaches for modeling the phenomenon. It's definitely a multidisciplinary field, and I think it's exciting.
Thank you.
Oh, can I just also add another reason why I think it's exciting is because from a very simplistic point of view, it's naturally a 2D problem. There are many cases in TO where we have to just simplify and start with 2D and then work up to 3D. But this can be from a very simplistic view as we're looking at an interface that starts out flat. And of course, it very quickly becomes a 3D problem and you can make it as complex as you want, but it's an interesting place to start at an interface that is flat.
I also had a question, Natasha, and that is there a sort of a size effect in wear? So if you look at the particular designs that you're getting, is it going to make a difference if you have the same design, but one design is twice the size of another one?
Yeah, so the limitations of the model itself, like the Arshard's wear law, is that there are limitations to that model that break down at the nanoscale. So we are limited by the mechanical models and mathematical models for wear in the regime where they break down, and so size effects come into play there.
Okay. Excellent. And then there is one last quick question from Ahmad Najafi, and that is, did you use the weighted sum method to build your multi-objective function? And if so, how did you select the weights?
So right now, what I presented was a thermal optimization with a wear constraint. So it's not formally multi-objective yet. That is something that we would do next as a next step, but we just ran out of time in terms of this PhD project. So we also did a sequential optimization where we previously optimized for run and wear, and then we took that design and looked at its thermal performance and optimizing the thermal performance. But multi-objective is what we would do next, and that isn't what we did here in this paper.
All right. Well, thank you once again, Natasha. Very interesting presentation. And let's move on to our last presentation of this webinar, and that is by Professor Bin Niu at Dalian University. Bin, if you could please share your screen and take the floor.
Yes, thank you.
Thank you.
So hope now you can hear me and see the screen.
Yes, we can.
Okay, thank you. So good morning or good night or good afternoon, everyone. So my name is Bin Niu, and thanks Julia for the invitation. So I come from Dalian University in China. I think first of all, I want to thank my collaborators, Mr. Shan and Feng. They are my students, former students and current students. Also Professor Alec Lund from Aalborg University, Denmark. So the title of my talk is Discrete Material Optimization of Vibrating Composite Plate and Attached Piezoelectric Fiber Composite Patch. You will see, so I will talk something about the vibrations, and we will consider composite structures and together with some kind of smart materials. So we do optimization for both. So the spot structure and some smart materials on top of it. So here are the outlines. So I think I will quickly go through some vibration modeling, and I will introduce the optimization and some examples. So first of all, everyone knows vibration may have some certain harmful effects. So here are some reference they will see. So I think important things is from optimization point of view, we already see quite a lot of work. So I'm sorry for the incomplete list. So we know from optimization, we can optimize the material distribution of the structure itself. Here are some examples. In another ways, we also can use some piezoelectric intelligent material or smart material, you can call it, to realize the optimization of a structure, to reduce the vibration, to realize the vibration suppression. But in this talk or in this work, we will consider the composite structures. So here's just like here, we will optimize the stacking sequence, fiber angle, and also we also try to do optimization to optimize the selections of materials. Then at the same time, so we also apply some kind of MMC. MFC's patch, we call it a piezoelectric patch. They also have some fiber. It also have some directions. So we optimize both the support structure and the piezoelectric patches. So first of all, there are some analysis model for this kind of piezoelectric material. We know it has the positive effect, also inverse or converse effect. So it can realize the conversion from mechanical energy to the electrical energy or inverse. So we have some model, so you can consider the elastic, also the electric equations of this kind of material, and after some derivation, you will get the force and electric coupling equations. But in this work, we do some kind of simplification. This means we neglect the positive piezoelectric effect. This means we only consider the converse piezoelectric effect. So we consider this like a piezoelectric material as some kind of actuator, so we can get this piezoelectric induction force. So for vibrations, we can from the standard this vibration equation, then we can just introduce this piezoelectric induction force here. Then we get a new equations. Of course, when you apply this kind of piezoelectric patches, you will introduce some mass or damping or stiffness contribution to the equations. So, and sometimes we use the standard really damping model. So now we have these equations for the analysis. We can build our optimization model. Then the objective, we are going to minimize the vibration response. Then here, I will talk about what kind of objective we will use. And here we use the DMO method. I will use the DMO afterwards. This is discrete material optimization method. Then this is the governing equation. We have some kind of mass constraint for both the support structure, also this piezoelectric material. Then we have this lower bound and upper bound for the design variables. So first of all, we introduce this DMO. DMO is developed by Eric Lund's group some years ago. So we know we can realize the material optimizations, then the structure can select the best from among several materials. So we can choose, for example, for the fiber, for common fiber materials, we can choose the different fiber angles from maybe discrete choices. And of course, we also can introduce this isotropic form as one kind of candidate material. Here, from the standard DMO, we do some development. We introduce for the mass density, for this constitutive relation, also for this piezoelectric constant matrix. So we have this Kc. Kc is some kind of penalty or penalization. We call it weight function. We can try to do some kind of penalization to realize the optimum choices of materials. So here the objective, we use input energy. This is the input power of our cycle. So this is we can get the distribution of the vibration. If we minimize this objective, we can minimize the vibration response of the structure. We use the adjoint method to derive the analysis, the sensitivity analysis of the objective. So here we give one example. So this is the 6 layers plate, 6-layer laminated plate. So on the top layer, this is the piezoelectric layer. So on the bottom from maybe 1 to 5, this is a support, how we call the base structures. They are laminated composite structures. So we have 6 layers. On the bottom, the first layer, we only allow this fiber material. This means we can choose the material 0 degrees, 45 or 90 or maybe 135 degrees. This is for the bottom layer. And from 2 to 5, the layer 2 to 5, we can allow this fiber materials. At the same time, we also allow one foam material. This means we can select different materials for the number 2 to number 5 layers. On top layers is piezoelectric materials. We know this is also some kind of this fiber material. This means they also have the fiber orientations. We also allow 0, 45, 90, and 135 degrees. And at the same time, we can realize topology optimization for this kind of piezoelectric materials. This means we allows void on top layers. So here's the modeling. We consider the different excitation frequencies because we consider the vibration problem. And this is the response frequency of the initial design. This can be used as a reference. So first of all, we see some optimization results. Then we applied 100 Hertz, and we also applied some voltage for the piezoelectric layers. Here's the optimized design. We see this indicate the fiber orientation. And in the layer 2 to layer 5, there are some void. In white, this means the foam material is selected, but on the top layer, on the layer 6, this is indicated that this is in void, no material. This is in blue. This means the fiber angles for the piezoelectric layers. So from the optimization, we can see the objective has been reduced significantly. Then we also consider different excitation frequency. Here's 200. Then you will see the topology is quite different. Then I think due to time, we can just say some kind of displacement amplitude of the vibrations. This is 100 and 200. This is initial design. This is the voltage is not applied to the optimized design. So this means after the applying the voltage, then we will say this the vibration has been reduced significantly. This also means the electric effect is very important for this kind of vibration control. So of course, for this design, you will see the fibers, they have some kind of very sharp change between the elements. So we introduce some kind of patch design. The basic idea just to force the design variables in a region to be the same. Of course, here just to give a very simple examples. Maybe 4 design variables we can force just to be the same. After this very simple patch design, we can do some change to the sensitivity analysis. Then we can have some change for the top layers. The other layers, we didn't use this patch, but only on the top layer for these piezoelectric layers. Then we will say these 4 elements, we choose the same fiber angles. This we have more regular fiber choices. This is for 100, for 200, we get the similar regulars, but the topology is very different because it's related on the vibration of the structure. Also, that we can just show the comparison of the optimization results. We use this kind of patch or no patch. We will say after optimizations, the reduction rate or the reduce of the objective is very similar, only slightly changed. This means we use this patch. We use the patch. We can get more regular piezoelectric layer, but the objectives almost the same. So finally, we have some concurrence on the studies. So in these studies, we use this DMO, discrete material optimization method, to the vibration problem of the composite structures with some kind of piezoelectric effects or piezoelectric layers. So secondly, we introduce this patch. We can get more regular. And we also have some discussion about the excitation frequencies, also discussion about the voltage effect if we only consider the stiffness of the structure of these piezoelectric layers and don't consider the converse electric effect. So anyways, here's the some summary. If you want to know the more details, you can go to our paper. It's published in JAMA in 2019. Thank you very much.
Thank you very much, Ben. Are there any questions for Ben? You can either type them in the chat or unmute your mic and ask them directly. I have one question, Ben. So I'm curious about the fact that introducing the patches gave you a very similar solution. And I'm wondering if that is some sort of indication of whether this particular problem has many local minima, or I was also wondering about whether there is any sort of mesh dependency if you don't introduce these patches.
I think, Julian, I think the second point maybe works because the patch right now is not so large. We didn't consider two large regions have the same design variables, just a little bit small. So it's not so big difference, just maybe 2 elements or 4x4 elements. Compare the structure is still very small. So from this effect, I think that's the reason for the patch designs. The objective is not so big difference. Another thing is we only introduce the patch on the top layers only for the piezoelectric layer. So the other layers we still just we can choose the fiber for freely for each element. We didn't introduce any filter or any patch on other layers. So this is only on top layer, on this piezoelectric layers. Maybe I can stop the sharing.
We have one question in the chat from Elahe Hadavi, and the question is if you could please introduce or describe some possible applications for these structures.
Yeah. Okay. Thank you very much. I think we have in our small lab we have very small this structures. It's like a beam. We can use this piezoelectric and like MFC. This is some commercial patch. You can buy it and attach or bond it on some kind of the structures to control the vibrations. It can reduce the vibration or suppress the vibration. This is one kind of lab testing. I think in real life, and right now people already use this MFC. MFC's this piezoelectric materials widely for the vibration control or deformation control. This is be used, but to some extent, this is the choices is still limited. They just provide you, or you can buy at least a certain type or certain size of this kind of material. I think maybe in the future it can be produced or manufactured by freely, I think, without too much limit. And at least for this fiber material or fiber, there are some, but for the isotropic, this piezoelectric material, you can just produce any shape or any size. That can be, I think, directly related to this topology optimization. For this fiber, this is anisotropic piezoelectric material still have some limited by the size, by the type. But I think it can be used for many quite other fields in related to the vibration or deformation control. And at least this is my understanding.
All right. We do not have any more questions, so I think we can conclude our webinar today. Let me thank once again all of our speakers, some of whom are joining at a time that is very late in the evening, like Ben and Tsuyoshi, so we really appreciate your time. I'd like to remind our audience that the recording for the webinar will be available afterwards in the Top Webinar website. And with that, thank you, everyone, and have a good good rest of day, afternoon, or evening, depending on where you are. So thank you very much.
I have a request for the speakers. It would be nice if you can send me your slides, so I will post to the Topology Optimization webinar, the website. Yeah, I will send you an email later. Yeah.
Okay.
Yeah. Thank you for joining us. See you next time.
See you.
Thank you. Thank you.
Thank you very much.